Right now, the fastest object humanity has ever sent into space moves at a speed that almost refuses to fit inside ordinary thought. The Parker Solar Probe, built to study the Sun from closer than any previous spacecraft, reaches a peak velocity of roughly 430,000 miles per hour during its deepest solar approaches. That number sounds less like transportation and more like an assault on common sense. At such a pace, a machine could circle Earth in only a few minutes. It could cross continents in seconds. It could outrun nearly every comparison the human mind normally uses to understand motion. And yet, when this extraordinary speed is placed against the true scale of space, it begins to look small, almost still, like a drifting grain in an ocean too vast for instinct to measure. This is the first and most important fact in any honest attempt to understand how far a human being could travel in one lifetime. The modern age has learned how to move fast by the standards of Earth, but Earth is not the measure that matters. The cosmos is, for most of human history. Speed remains intimate and local. A walking body, a running animal, a sailing ship, and later a train or aircraft all belong to a world where journeys are measured against landscapes, coastlines, and weather. Even the great revolutions of motion remain tied to a planetary scale. A horse can outrun a person. A train can outrun a horse. A jet can cross oceans in hours. A spacecraft can leave the atmosphere entirely. Each step seems immense from within the world that produces it. The first satellites appear miraculous. The Apollo missions seem to break all historical limits at once. Human beings ride to the moon and return through Earth's atmosphere at tens of thousands of miles per hour, moving faster than any people before them. Yet each increase in speed, dramatic as it feels, happens inside a very small neighborhood. It happens inside the thin shell of human expectation formed by life on one planet orbiting one star. The Parker Solar Probe stands at the outer edge of that story. It is not carrying human passengers. It is not built for comfort, return, or survival. It is a specialized machine following a path that dives toward the Sun, protected by a heat shield while gravity and repeated flybys of Venus help build its astonishing velocity. This achievement represents decades of engineering, precise orbital planning, and a deep understanding of celestial mechanics. It is not speed gained by brute force alone. It is speed borrowed, shaped, and carefully assembled from the motion already present in the solar system. In one sense, it marks a triumph. In another, it reveals a limit. When the fastest object humanity has built still remains trapped inside the immediate family of the Sun, the imagination begins to feel the size of the wall ahead. The wall is not made of metal, politics, or money. It is made of distance itself. Distance in space behaves differently from distance on Earth. On Earth, movement usually compresses the world. Roads turn mountains into weekends and oceans into flights. In space, movement often does not compress anything enough. The scale grows too quickly. Empty regions become meaningful obstacles simply because there is so much of them. A human life, even a long one, is short beside these expanses. 80 years sounds substantial in ordinary life. It can hold childhood, work, memory, age, and the slow accumulation of experience. But if that entire span is devoted to continuous travel at the greatest speed humanity has yet achieved, it still carries the traveller only a tiny fraction of the way to even the nearest stars. This is the disorienting truth that begins the journey. The problem is not that human technology has done little. The problem is that space is enormous beyond comfort. The Parker Solar Probe gives this truth a face. Its speed is real. Its motion is measurable. Its engineering is among the finest humanity has produced, and still it serves mainly as a lesson in propulsion. The machine seems fast because human intuition forms in streets, weather, and horizons, not in interstellar darkness. The mind naturally reacts to large numbers with awe, but awe is not the same as scale. A speed that appears almost absurd within the atmosphere of Earth becomes modest when set against the gulf between stars. This mismatch between feeling and reality sits at the center of the subject. It is why discussions of cosmic travel often drift into fantasy so easily. Numbers can be spoken without being understood. Millions, billions, and light years can pass through language while leaving instinct untouched. What matters here is not merely that current spacecraft are fast, but that their speed fails to transform the nature of the journey. They remain creatures of the solar system. They move within the reach of sunlight, planetary gravity, and the long extended influence of the star that formed them. Even the most advanced probes do not yet belong to the larger galaxy in any practical sense. They are still close to home. This first region of the story, then, is not really about triumph alone. It is about contrast. Human beings have climbed from feet and sails to rockets and solar probes in a span so brief that history can hold it in a few pages. The increase in speed is astonishing. The increase in reach is far less complete. A machine can now move at hundreds of thousands of miles per hour, and that still does not place another star within a single human lifetime. The beginning of cosmic travel is therefore not a story of freedom. It is a story of perspective. The fastest object humanity has ever built does not prove that the stars are close. It proves that they are far. It does not show that the road is open. It shows how little of the road has been crossed. In that realization, something important becomes clear. Any serious answer to the question of how far a human could travel in one lifetime must begin not with dreams of distant galaxies, but with the hard-measured speeds already achieved and the sobering fact that even these speeds barely loosen humanity from the immediate surroundings of its own star. The nearest star beyond the Sun appears close only because human vision is generous with points of light in the night sky. The stars seem arranged on a dark surface, bright but somehow manageable, as though they belong to one high ceiling spread over Earth. This impression is useful for navigation and beauty, but it hides the truth that matters most for travel. The stars are not placed on a nearby shell. They are scattered through depth so great that even the closest among them lies at a distance that defeats almost every ordinary comparison. Proxima Centauri, the nearest known star to the Sun, is about 4 1/4 light-years away. That phrase, light year, does not describe time in this context. It describes distance. The distance light crosses in 1 year while moving through a vacuum at the fastest speed nature allows. Light is so swift that it circles Earth many times in a single second. It crosses the gap from the Sun to Earth in a little over 8 minutes. Yet even light, moving with this unmatched speed, requires more than 4 years to bridge the space between the Sun and Proxima Centauri. Once that fact settles into place, the local stellar neighborhood changes character. It no longer feels like a nearby archipelago waiting for ships. It feels like a sparse wilderness with islands separated by gulfs far beyond instinctive scale. If a human being was somehow placed aboard the Parker Solar Probe and allowed to maintain its greatest speed continuously, the journey to Proxima Centauri would still require thousands of years. The exact number matters less than what it means. It means the voyage would outlast empires, languages, political systems, and perhaps whole species. It means departure and arrival would not belong to the same civilization. The traveller would never arrive in any personal sense because the span of one human life would end long before the destination even began to feel close. This is why the nearest star problem is so important. It is not merely a question about one destination. It is the first clear proof that interstellar travel is not an expanded form of travel within the solar system. It is a fundamentally different category of movement. A spacecraft that can cross the distance from Earth to the Moon in days, or the distance to Pluto in years, still fails completely when asked to cross even the smallest meaningful gap between stars. The mind resists this because it wants continuity. It wants to believe that bigger engines and more patience will scale up the familiar pattern. But the numbers refuse that comfort. The nearest star is not a slightly harder version of Mars. It is a different order of challenge. A human lifetime at current peak spacecraft speed covers only a tiny fraction of the road. That fraction sounds impressive in miles, but cosmic distance does not care how a number feels when spoken aloud. It cares only about the ratio between what is crossed and what remains. And in this case, almost all of it remains. Even this nearest stellar distance exists inside what astronomers would still call a very local region. Proxima Centauri is part of the Alpha Centauri system, a neighbouring stellar family drifting through the same broad galactic environment as the Sun. It is not an exotic destination at the edge of the Milky Way. It is next door by cosmic standards. If next door already lies beyond the natural span of one life at our fastest achieved speed, then the rest of the galaxy becomes something else entirely. Barnard's star, Sirius, Epsilon Eridani, Tau Ceti, and other familiar nearby stars remain close enough to be named individually in catalogues and textbooks, yet far enough that journeys to them by present methods belong more to geology than biography. They unfold on timescales more appropriate to erosion, glaciation, or evolutionary change than to any traveller's living memory. The concept of a voyage begins to break under that weight. Travel usually implies an arc that a person can inhabit. There is departure, passage, anticipation, and arrival. There may be hardship, but there is still continuity of self across the route. A trip that requires thousands or tens of thousands of years does not preserve that continuity for a biological human being. It becomes instead the motion of an artifact, a lineage, or a message. This distinction is essential. Humanity may send probes, archives, or perhaps one day multi-generational vessels toward nearby stars, but that is not the same question as how far one human could travel in one lifetime. That question is narrower, more intimate, and far harsher. It asks what distance can fit inside the aging of one body and one consciousness. The answer, under present-day velocity, is almost unbearably small. This does not mean the stars are unreachable in every possible sense. It means they are unreachable in the ordinary human sense of going there and still being oneself upon arrival. That limitation changes the emotional structure of cosmic ambition. The night sky has inspired myths, calendars, religions, and science because it invites the mind outward. Yet the first genuine outward step beyond the solar system already exposes a barrier that is deeper than enthusiasm. It is a barrier of duration. Human beings are not only limited by speed, they are limited by mortality. The nearest star problem is where these two facts meet. A machine may continue for millennia, a human being does not, and so the local stars, which look like lanterns scattered near the edge of vision, become markers of a profound divide between what can be seen and what can be lived. To stand on Earth and understand this clearly is to experience a quiet shift in perspective. The universe does not begin denying human ambition at the edge of the galaxy. It begins denying it at the nearest star. The first step outward is already larger than a life. The gap is already deep enough to separate present technology from personal arrival. Every later discussion about advanced engines, relativity, or future civilizations rests on this plain foundation. Before any loophole is opened, before physics reveals its more subtle permissions, the nearest stars establish the scale of the problem with cold clarity. They show that the ordinary meaning of travel fails almost immediately beyond the sun's neighbourhood, and that any path to the wider cosmos must confront not only distance, but the briefness of human time. Beyond the familiar planets and their moons, the solar system does not end cleanly. It fades, it thins, it becomes less a set of obvious worlds and more a gradually weakening domain of influence spread across darkness. This outer region matters because it reveals how difficult it is not merely to reach another star, but to leave the sun behind in any complete sense. Human imagination often pictures the solar system as a neat arrangement beginning with Mercury and ending somewhere beyond Neptune. In diagrams for classrooms, the planets sit in tidy order, and beyond the last major orbit the page simply stops. Reality is much less tidy. The sun governs a far larger structure than the visible row of planets suggests. Its gravity extends outward through a vast volume populated by icy bodies, scattered debris, and the faint remains of formation processes that took place billions of years ago. Even the space beyond the planet still belongs, in important ways, to the sun. The first outer boundary often discussed is the heliosphere, the enormous bubble carved into interstellar space by the solar wind. The solar wind is a continuous flow of charged particles streaming outward from the sun. As it moves away, it pushes against the extremely thin gas between the stars. This creates a region where the influence of the solar wind dominates local conditions. The heliosphere is not a rigid shell. It changes shape under the pressure of the interstellar medium and the motion of the sun through the galaxy. Still, it provides a meaningful boundary between the immediate plasma environment shaped by our star and the broader interstellar surroundings beyond it. When Voyager 1 crossed the heliopause in the year 2012, many headlines announced that it had left the solar system. The statement carried some truth, but not the whole truth. Voyager 1 had passed beyond the zone where the solar wind strongly controls conditions. It had entered interstellar space in a physical and measurable sense, yet it had not escaped the sun's gravity, nor had it passed beyond the immense reservoir of icy objects believed to surround the planetary region at far greater distances. In that deeper sense, it remained within the sun's long extended domain. This distinction matters because language often hides scale. To say that Voyager entered interstellar space sounds like a decisive departure, but the farther one looks, the more that departure resembles the first step from a doorway into a field rather than the end of a journey. Beyond the heliosphere lies the region associated with the Oort Cloud, a vast and still partly inferred shell of icy bodies extending tens of thousands, and perhaps up to 100,000 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. Even that single unit is already enormous by human standards. To multiply it into the tens of thousands is to leave intuition behind almost completely. The Oort Cloud is thought to be the source of many long-period comets, ancient frozen bodies that can spend millions of years tracing immense loops before occasionally falling inward toward the warmth of the sun. These objects are not arranged in a flat planetary disk like the major planets. They likely form a loose spherical distribution, a remote halo marking the outer reach of the sun's gravitational possession. This means the solar system is not only wider than it seems, it is deeper and more diffuse. It has outskirts so remote that sunlight there becomes weak, and the sun itself shrinks to just another bright star among many. A traveller moving outward would not encounter a sign announcing the true end. There would be no gate, no final planet, no ceremonial edge. There would only be diminishing sunlight, longer orbital periods, colder matter, and a gradual transition from one form of belonging to another. The difficulty of leaving this environment becomes clear when time is placed back into the picture, at current spacecraft speeds. Reaching even the inner parts of the Oort Cloud would require centuries. reaching its outer extent would require far longer than any human civilization has yet endured in recognizable continuity. This means that a human lifetime spent travelling outward at present achievable speeds would not truly leave the solar system in the fullest sense. It might pass the planets, it might pass the heliosphere, it would still remain within the sun's gravitational kingdom. The traveller would die before crossing the long twilight where the sun's hold finally gives way to the larger galactic field. This is one of the most sobering truths in all of spaceflight. The outer solar system itself is already too large for present human-scale travel. Before interstellar travel can become personal, even departure from home must be reimagined. The local cosmic neighbourhood is not a small front yard. It is an enormous layered structure whose outskirts already exceed the natural time horizon of an individual life. Seen this way, the solar system becomes less like a cluster of nearby worlds and more like a province with a fading frontier. The planets occupy only the inner settled zone. Beyond them lie scattered populations of small bodies, reservoirs of ancient ice, and the outer pressure boundary where the sun negotiates with the galaxy. Farther still lies the probable cloud of cometary debris that records the ancient violence of formation and migration. The whole structure is a reminder that human beings evolved in a tiny warm pocket of a much larger domain. To leave that domain completely requires more than courage or engineering skill. It requires an ability to conquer duration. Every mile outward adds not just distance but estrangement from familiar scales. By the time one reaches the edge of the sun's wider family, the concept of a voyage has already begun to exceed the frame of individual life. The solar system, viewed from within, often feels intimate because its planets are named and known. Viewed as a layered physical system with a heliosphere, scattered disk, and distant comet cloud, it becomes something else, the first vast region a traveller must outgrow before the stars can even be approached, and under present conditions, that first act of departure is already unfinished. The reason ordinary rockets fail is not hidden in a missing invention or a neglected budget line. It is written into the physics of propulsion itself. A rocket moves by throwing mass in one direction, so that the vehicle moves in the other. This is a clean and elegant consequence of momentum conservation, and it works everywhere from fireworks to deep space probes. Hot gas is expelled backward, and the rocket is pushed forward. That principle has carried humanity from the launch pad to the moon and beyond. It is one of the great practical triumphs of physics. Yet the same principle contains a severe limitation that becomes more punishing as distance increases. A rocket must carry the material it plans to throw away. The faster it hopes to go, the more propellant it must carry. But carrying more propellant makes the rocket heavier, and a heavier rocket requires still more propellant to accelerate that added mass. This recursive burden is the heart of the problem. It means a rocket is not simply a vehicle with fuel in a tank. It is a machine trapped in a feedback loop where ambition multiplies weight, and weight multiplies required fuel. The mathematics describing this burden are captured in the rocket equation, developed in the early 20th century. The equation connects the speed a rocket can gain to two main quantities: the speed at which its exhaust leaves the engine and the ratio between its starting mass and its final mass after much of the fuel has been burned away. The logic is straightforward enough to state in plain words. A rocket performs well when it can throw exhaust very fast, and when a large fraction of its initial mass is expendable propellant. The difficulty appears when these requirements are pushed toward interstellar goals. Chemical reactions, even the most energetic useful ones, release only limited amounts of energy compared with the needs of cosmic travel. Hydrogen and oxygen can produce powerful engines. They can lift payloads from Earth and send missions across the solar system, but the exhaust velocity of chemical propulsion remains far too low for journeys to nearby stars within one human life. The chemistry itself sets the ceiling. The molecules leaving the engine cannot be made arbitrarily fast by enthusiasm or clever design. Better engineering can improve efficiency, but it cannot transform chemical energy into something it is not. This is where the dream of simply building a larger rocket collapses. Each additional increase in desired speed demands more propellant, and the amount required grows not in a gentle straight line but with brutal acceleration. The rocket equation punishes high velocity with exponential severity. A vehicle designed to reach modest planetary destinations can still be practical, because the needed speeds are limited. A vehicle designed to reach even a small fraction of the speed of light becomes absurd under chemical propulsion. Most of its mass would need to be fuel, but then most of that extra fuel would exist largely to accelerate other fuel. Very quickly the ratio becomes monstrous. The payload shrinks into insignificance, while the required starting mass expands beyond anything physically or economically meaningful. The machine begins to resemble a collapsing idea rather than a workable design. This is why the failure of ordinary rockets is not a temporary engineering embarrassment. It is a structural mismatch between the energy available in chemical bonds and the velocity demanded by interstellar space. Inside the solar system, rockets succeed because the distances, though immense, remain within a range where careful trajectories, gravitational assists, and patience can compensate for limits in raw propulsion. Between the stars, those same methods lose the argument almost immediately. To reduce travel times from thousands of years to decades requires far more than improving launch systems or refining engines by small percentages. It requires a different level of exhaust velocity and a different scale of energy entirely. Chemical rockets simply do not inhabit that regime. They belong to an age of local exploration, not an age of starflight. This truth can feel disappointing because rockets are visually dramatic. They seem to embody force, progress, and escape. A launch from Earth shakes the ground and tears fire into the sky. It appears to be the very image of power, but the deeper physics is quieter and less forgiving. The spectacle of launch says little about what happens after the fuel is gone and the long empty distances remain. A rocket may leave Earth magnificently and still be almost helpless against the scale of the galaxy. Its engine burn lasts minutes, perhaps hours in some configurations. The journey lasts years, centuries, or millennia. Most of the voyage is silence following a brief act of expenditure. This is one reason interstellar travel cannot be solved merely by scaling up what already exists. The familiar rocket is optimized for escaping gravity wells, changing orbits, and reaching planets. It is not designed for crossing the abyss between stars in personally meaningful time. The farther the destination, the more obvious this becomes. To ask a chemical rocket to carry a human to another star within one lifetime is like asking a rowing boat to cross an ocean by becoming slightly larger with each redesign. There comes a point where the method itself is the limit. That point arrives very early on the cosmic scale. Understanding this does not diminish the achievement of rocketry. On the contrary, it clarifies it. Rockets have opened the solar system to observation. They have carried instruments, landers, telescopes, and people beyond Earth. They have transformed humanity from a species bound to one world into a species capable of physically touching other worlds. That is extraordinary. But extraordinary is not the same as sufficient. The same physics that makes rockets so useful nearby also makes them deeply inadequate for the next leap. The road to the stars demands either propulsion with vastly higher exhaust velocity, access to much greater energy density, or a way of reframing the problem altogether through the structure of space and time. Ordinary rockets cannot provide that passage. They can begin the story, but they cannot finish it. They carry human ambition to the threshold of the larger universe and then reveal, with absolute honesty, that another principle will be needed. Once chemical rockets reveal their limits, The natural response is to look for better engines rather than abandon the journey. This search has produced some of the most elegant and inventive ideas in the history of astronautics. Each one offers a real improvement. Each one teaches something important about how motion through space can be shaped. Yet each one also arrives at the same quiet conclusion when measured against the span of a single human life. The gains are meaningful inside the solar system, but they do not dissolve the deeper problem of interstellar distance. Gravity assists are the first of these improvements, and in some ways the most beautiful. A spacecraft can pass close to a planet and borrow a small amount of that planet's orbital momentum. The planet loses an amount too tiny to notice, while the spacecraft leaves on a faster trajectory. This method has already transformed real missions. The Voyager spacecraft used giant planets as stepping stones to reach the outer solar system. New Horizons received a major boost from Jupiter on its way toward Pluto. The Parker Solar Probe uses repeated encounters with Venus to reshape its orbit and deepen its dives toward the Sun, where gravity helps build its record speed. Gravity assists feel almost magical because they allow a spacecraft to gain velocity without carrying extra propellant for the entire increase, yet they depend on a limited resource. The solar system contains only so many useful planets in helpful positions, and the geometry of these encounters is constrained by orbital timing. A spacecraft cannot harvest unlimited speed by repeating the trick forever. The boosts are real, but the ceiling remains far below what a human lifetime would need for travel to the stars. Ion propulsion offers another genuine advance. Instead of relying on hot chemical exhaust alone, an ion engine uses electric fields to accelerate charged particles, usually from a noble gas such as xenon, to much higher exhaust speeds. This makes the propulsion system far more efficient in its use of propellant. A spacecraft can continue thrusting very gently for months or years, gradually building substantial changes in velocity. Missions such as Deep Space One and Dawn demonstrated that this method works. Dawn in particular showed how ion propulsion can reshape trajectories with a patience chemical rockets could never match, allowing a single spacecraft to visit more than one major body in the asteroid belt. But the improvement comes with a trade. Ion engines are efficient because they throw little mass very fast, yet the thrust they produce at any moment is tiny. The force is so small that it would seem almost trivial in daily life. In space, where resistance is absent and time can be generous, that small force matters. For rapid human travel, it does not come close to enough. Ion propulsion is excellent for robotic missions that can afford to wait. It is not a path that makes interstellar voyages fit comfortably inside a biological lifetime. Nuclear thermal rockets move a step higher on the ladder. These systems would use a nuclear reactor to heat a light propellant, often hydrogen, and expel it through a nozzle. Because the energy source is much more concentrated than chemical combustion, the exhaust velocity can be significantly better. During the 20th century, programs such as NERVA showed that the concept was not fantasy. Test engines were built and operated. The physics is sound, and the performance could shorten travel times within the solar system in useful ways. A nuclear thermal spacecraft might cut months from Mars missions and open more ambitious patterns of exploration. Yet even here, the numbers remain merciless when the destination becomes another star. Doubling or even tripling performance over chemical propulsion is impressive in engineering terms, but cosmic distances are not impressed by engineering terms alone. A journey to the nearest stars would still require many thousands of years. Better does not become enough. Solar sails may be the most graceful of all the serious concepts. They do not burn fuel at all. They allow sunlight itself to push a large reflective sheet through space by transferring momentum from photons. The force is delicate but constant. Over time, in the inner solar system, it can build useful speed. Missions such as Icaros proved that this is not merely a thought experiment. Light can indeed propel a spacecraft. The appeal is profound. A sail does not carry the huge propellant burden of a rocket. It receives its push from the star already shining at the centre of the system. Yet the weakness of sunlight appears as soon as distance increases. The farther a sail moves from the sun, the weaker the radiation pressure becomes, dropping rapidly with increasing distance. The acceleration that seems promising near the sun fades in the outer regions and becomes negligible in interstellar space. A solar sail might eventually reach remarkable velocities by the standards of past missions. But even then, the travel time to the nearest stars would still run into thousands of years. The pattern is now unmistakable. Gravity assists exploit the motion of planets. Ion engines use propellant more wisely. Nuclear thermal rockets draw on denser energy sources. Solar sails remove onboard fuel from the equation entirely. These are not failures. They're clever and serious expansions of what spacecraft can do. They widen humanity's operational reach, reduce travel times within the solar system, and prepare the technical imagination for more advanced concepts. But none of them solves the human lifetime problem. They improve the local map without changing the nature of the larger ocean. A traveller using these methods may reach farther, faster, and with greater elegance than before, but still not far enough to turn nearby stars into destinations that belong to one living person's natural span of years. This is why each better engine teaches the same deeper lesson. The issue is not only propulsion quality, it is the ratio between every plausible near-term speed and the enormity of interstellar space. Progress remains real, but the scale of the problem outruns it. Humanity can refine its machines, borrow momentum, ride sunlight, and split atoms for heat, and still remain largely confined to the sun's neighbourhood when measured against one mortal life. The road outward is lengthened not by lack of ingenuity, but by the sheer vastness it crosses. The barrier that now comes into view is unlike the earlier ones. The limits of chemical rockets, gravity assists, ion drives, nuclear thermal engines, and solar sails all arise from practical physics, from how much energy can be released, how much propellant can be carried, and how efficiently motion can be sustained. The next limit is deeper. It is not merely a limitation of current machines, it is a rule woven into the structure of reality. This is the light speed barrier. In modern physics, light in a vacuum travels at a constant speed that is the same for all observers, regardless of how either source or observer is moving. That statement sounds simple when spoken aloud, but it carries consequences that overturn ordinary intuition. In daily life, speeds seem to add together in straightforward ways. A ball thrown forward from a moving train appears faster to someone standing beside the tracks than to a passenger on the train. Motion feels relative and easy to combine. Light does not behave that way. Its speed remains fixed, and because that speed is fixed, the universe adjusts other things instead. Space and time themselves become flexible in order to preserve this constancy. Before those strange adjustments can be understood, the barrier itself must be faced plainly. No object with mass can be accelerated to the speed of light. It can approach that speed ever more closely, but it cannot arrive there. The closer it gets, the harder each further increase becomes. This is not because the object encounters a physical wall or some hidden drag in empty space. It is because the energy required for additional acceleration rises without mercy as velocity climbs toward the speed of light. The barrier is not a cliff. It is an infinite slope. One can move up it, but each step costs more than the last, and the final height can never be reached. This transforms the entire question of travel. If faster and faster motion always remained merely an engineering challenge, then one could imagine progress continuing until distances between stars became manageable. but the speed of light stands as a ceiling that no material traveller can cross. Even if perfect engines were invented, even if energy became far cheaper and more abundant than anything known today, even if spacecraft were built with ideal efficiency, the barrier would remain. It belongs not to human weakness, but to the design of the cosmos. This is why the light-speed barrier changes the emotional tone of the story. The earlier sections show that present methods are inadequate. This section shows that even the dream of simply going arbitrarily fast has a limit beyond which nature does not permit passage. The importance of that limit becomes clearer when one remembers the scale of the distances involved. A light year is already the distance light itself travels in 1 year. If even light needs more than 4 years to reach the nearest star, then no ordinary traveller moving below that speed can do better than 4 years in the frame of the outside universe, and in practice must do worse. The stars do not merely seem far, they are defined by the travel time of the fastest phenomenon allowed by known physics. This gives the cosmos a special kind of remoteness. There are barriers in life that can be crossed with enough effort, wealth, or invention. The light-speed barrier is different. It does not negotiate. It does not care what civilization has built. It establishes a universal order in which every journey must remain slower than light itself. At first, this sounds like the end of the subject. If no traveller can outrun light, then perhaps the stars are simply too far away for any personal voyage. That conclusion once seemed natural to many physicists and writers. It appeared that biology and relativity together had formed a prison. Human life is short. The stars are distant. The speed of light cannot be reached, much less exceeded. Therefore, a human being must remain trapped within a tiny region around the sun. This line of thought is understandable, but it is not the whole story. The light-speed barrier closes one door while opening another much stranger one. Because the speed of light is fixed, the universe preserves it by changing how time passes and how distance is measured for fast-moving travellers. In ordinary life, those effects are too small to matter. In the realm of extreme velocity, they become decisive. Yet before that hidden permission can be explored, it is necessary to feel the barrier fully on its own terms. A spacecraft moving at half the speed of light would already be unimaginably fast by all standards of modern engineering. At 9/10 of light speed, it would enter a domain far beyond any present or near-future human machine. At 99% of light speed, it would seem almost to have conquered the cosmos. And still it would remain below the limit, still unable to touch the final boundary, still subject to the increasing cost of every additional fraction gained. The light-speed barrier therefore defines not only what cannot be done, but the region in which all meaningful future star travel must occur. Any realistic interstellar civilization would live in the long narrowing approach below the limit, never beyond it. This realization also changes how empty space is imagined. Space is not simply a passive backdrop through which anything may move at any chosen speed. It is structured. It has rules. Time and distance are not fixed scaffolding around events, but part of the same order that gives light its special status. The barrier announces that motion at the deepest level is connected to the nature of space-time itself. This is why it cannot be overcome by stronger materials or bigger engines alone. To confront it is to confront the architecture of the universe. And yet, within that architecture, something remarkable waits. The very law that forbids reaching light speed also begins to reshape time for the traveller who moves fast enough. The prison, it turns out, is not built quite the way it first appears, but before the hidden opening can be entered, the boundary must be respected. The speed of light remains the great divider between human intuition and cosmic truth, the absolute limit that ends one kind of dream and prepares the mind for a more subtle one. In the early years of the 20th century, the light-speed barrier stops being only a limit and begins to reveal a hidden structure beneath ordinary experience. Albert Einstein shows that the constancy of light is not an isolated curiosity, but the key to a deeper reordering of motion, distance, and time. The result is special relativity, a theory that does not remove the cosmic speed limit but changes what travel means near that limit. The essential idea is quiet and radical at once. Time does not pass identically for all observers. It depends on motion. A clock moving at very high speed relative to another clock ticks more slowly when viewed from the slower frame. This effect is called time dilation. In daily life, it is too small to notice. A walking person, a racing car, or even a jet aircraft moves far too slowly for the difference to matter in ordinary experience. But the effect is still real. Precise atomic clocks carried on aircraft and satellites confirm it. The universe is already behaving this way all around human life, though the scale is usually too small to disturb intuition. Once velocity rises to a substantial fraction of light speed, the effect grows from negligible to transformative. This is the loophole hidden inside the barrier. The traveller can never outrun light, yet the traveller's own experienced time can shrink relative to the time that passes outside the ship. A journey that seems impossibly long from Earth can become much shorter for the person making it. This does not violate the light speed limit. From the perspective of Earth, the spacecraft still takes years, decades, centuries, or more to cross the relevant distance. The outside universe still keeps its honest account. But aboard the moving vessel, time itself runs differently. The body ages more slowly relative to the people left behind. The traveller does not gain infinite reach, but gains something, almost as strange a life that can stretch farther across the cosmos than ordinary intuition first allows. The key quantity in this picture is often called the Lorentz factor, though its deeper meaning can be stated without mathematics. The closer a spacecraft moves to the speed of light, the more strongly time slows aboard it relative to the outside world. At modest fractions of light speed, the effect is noticeable but limited. At extreme fractions, very close to the limit, the difference becomes dramatic. A traveller moving at half the speed of light experiences time somewhat more slowly than people on Earth, but not enough to transform interstellar travel. A traveller moving at 9/10 of light speed begins to enter a different regime. A traveller moving at 99%, or 99.9%, of light speed crosses into a realm where years outside correspond to much shorter spans inside the ship. The journey remains long for the universe, but not for the traveller in the same way. This is one of the strangest and most beautiful results in all of science. The universe has not placed a simple wall around human ambition. It has built a more subtle system in which the speed limit remains absolute, while time itself becomes negotiable through motion. This means that the phrase "one lifetime" must be handled with care. If one lifetime refers to Earth time, then the stars remain stubbornly remote. If one lifetime refers to the traveller's own biological time, then the map begins to change. A human being could, in principle, reach destinations that seem far beyond the reach of 80 ordinary years, provided the ship can approach sufficiently high relativistic speed. The person aboard might age only decades while centuries or millennia pass elsewhere. The gap between human mortality and cosmic distance does not disappear, but it is reconfigured. Mortality remains. Distance remains. The relationship between them softens. Another effect accompanies time dilation and helps clarify why this is not merely a trick of clocks. Distances along the direction of the motion contract for the fast-moving traveller. From the traveller's perspective, the route itself becomes shorter. The star is still far away in the Earth frame, but the ship sees the intervening distance compressed. Time aboard is shorter, not because the traveller is deceived, but because space-time itself is organised so that different observers measure different intervals while agreeing on the deeper laws. This is why special relativity feels so unsettling at first. It asks human beings to give up the idea that time and distance are universal backdrops the same for everyone. Instead, they become linked to motion. The faster the traveller moves, the more severe the reshaping. For cosmic travel, this changes everything. Under ordinary expectations, a human lifetime seems locked to a small radius around Earth. Under relativity, the same lifetime, measured aboard a near-light-speed ship, may span far greater reaches. Yet this new freedom comes with conditions. The traveller is not escaping consequence. The years avoided aboard the ship still pass somewhere. Family, culture, language, civilization, and history continue on Earth or wherever departure took place. The shortened lifetime aboard the vessel is not a victory over time for everyone. It is a divergence of time between different paths through space-time. This gives relativistic travel its distinctive emotional structure. It is not simply fast movement. It is movement that separates personal time from the time of home. A traveller may preserve youth while the world behind grows old. The loophole is therefore real, but it is not free. It solves one problem while quietly creating another. Still, as a matter of pure possibility, the effect is astonishing. It means that the light speed barrier is not the end of the story, but the beginning of a new one. The stars remain far, but not equally far in every frame. The traveller's body need not experience the full length of the journey as measured by those left behind. Within the laws of physics, one human lifetime can be stretched outward by velocity itself. This is the first true opening through the cosmic prison that earlier reasoning seemed to build. The door is not in the wall. The door is in time. Once time dilation is accepted, the map of possible journeys begins to change in a way that is both mathematically precise and emotionally difficult to absorb. The change does not make space small. It makes experience duration flexible for the traveller. A destination that appears impossibly far from Earth can become reachable within a single human lifespan measured aboard a sufficiently fast vessel. The outside universe still keeps the full count of years, the star still lies where it lies, the ship still never exceeds light speed. Yet the traveller crosses the distance under a different measure of time, and this difference transforms what a lifetime can contain. The nearest stars are the first places where the effect becomes concrete. At speeds far below light, a trip to a nearby system remains an exile lasting many years or centuries even for the person aboard. But as the ship approaches a large fraction of light speed, the traveller's subjective time begins to compress enough that the voyage changes character. A star like Proxima Centauri, unreachable in one life by present methods, moves into a new category. A traveller could depart, endure a voyage measured in only a handful of personal years, and arrive still recognisably within a single continuous life. More distant stars then follow the same logic. Vega, one of the bright stars visible in the night sky, lies about 25 light-years away. In ordinary thinking, that places it well beyond the natural scope of a personal journey. Under relativistic motion, however, its distance can be crossed in a surprisingly short span of shipboard time if the velocity is close enough to light speed. The same principle extends outward to clusters and regions that previously belonged only to astronomical observation. The Pleiades, the famous blue cluster known in many cultures, sits hundreds of light-years away. Under non-relativistic travel, this is absurdly distant for a person. Under sufficiently extreme relativistic travel, the experience duration can fall into the range of years or decades rather than centuries. This is where the imagination begins to feel the true reach of the loophole. A human being is not limited to the tiny sphere defined by ordinary aging under ordinary motion. A traveller moving fast enough could cross the local stellar neighbourhood, reach brilliant nearby stars, enter clusters, and witness parts of the galaxy that would otherwise remain forever observational rather than experiential. The same reasoning can be pushed much farther. The centre of the Milky Way lies about 26,000 light-years away. There, around the supermassive black hole Sagittarius A star, conditions differ profoundly from those near the Sun. Star densities are higher, gravitational environments are more violent, radiation fields and stellar populations create a region unlike the quiet suburban orbit of Earth. From the perspective of ordinary time, the galactic centre is hopelessly remote. From the perspective of a traveller at an extreme relativistic speed, it becomes less hopeless, though still severe. If the ship can approach the speed of light closely enough, the experienced travel time can be reduced from tens of thousands of years to a span more comparable to a long human life or a sequence of generations. Push the velocity even closer to the limit, and the subjective duration shrinks further. The galaxy begins to reorganize itself not spatially, but temporally. Regions once separated by geologic spans begin to fit inside biography. The same is true for intergalactic distances in principle, though now the emotional cost becomes harder to ignore. Andromeda, the nearest major galaxy, lies about 2.5 million light-years away. In the Earth frame, nothing about that number becomes small. Any signal or traveller making the crossing still belongs to immense outside timescales. Yet for a traveller moving at an extraordinarily high relativistic speed, the experienced journey can compress into years rather than millions of years. That statement sounds almost impossible when first heard, but it is a direct consequence of the same time dilation that has already been confirmed on smaller scales. The equations do not stop at nearby stars. They continue outward with the same indifferent consistency, a human life, measured from within the ship, could in principle span not only stars and clusters, but even galaxies, provided the required velocity can be achieved and sustained. This is the moment where the idea of travel begins to detach from ordinary history. A person could leave Earth, reach another galaxy, and still arrive as the same consciousness that departed. But they would not arrive in the same era. The outside universe would have moved on by millions of years. Home would no longer be home in any recognizable sense. This reveals the double nature of relativistic journeys. They are triumphs of range and catastrophes of simultaneity. One can go far, but not remain anchored to the time that gave the journey meaning in the first place. Even within the Milky Way, the same pattern appears. A round trip to a distant cluster or the galactic centre may be survivable in subjective time, yet the Earth to which the traveller returns may belong to a future so remote that language, biology, and civilization have all changed beyond recognition. The farther the journey, the more complete this temporal separation becomes. In this way, relativistic travel expands one lifetime, while severing it from the common flow of everyone else's. Still, the physical promise remains extraordinary. It means the universe is not arranged so that consciousness must remain forever trapped near its birth star. The local stellar neighbourhood, nearby clusters, the galactic interior, even separate galaxies can all become reachable in principle by a single living traveller, not because the speed of light is broken, but because time itself becomes uneven between frames. The old question, how far could a human travel in one lifetime, now demands a careful answer. In Earth time, not very far beyond nearby stars unless many generations are involved. In traveller time, potentially astonishingly far. The map has not become smaller. The traveller's clock has become stranger. The farther relativistic travel opens the map, the more sharply it reveals its price. Time dilation makes extraordinary journeys possible in principle, but it does not make them cheap. On the contrary, The same physics that allows a traveller's lifetime to stretch across immense distances also demands energy on a scale that pushes current human imagination to its edge. This is where the promise of relativity meets its hardest resistance. The obstacle is no longer only speed itself, it is the cost of approaching that speed with any object that has mass. In ordinary life, the relationship between speed and energy seems manageable. A bicycle moving twice as fast does not demand unimaginable effort. A car travelling faster uses more fuel, but still within an intuitive range. At low speeds, motion behaves according to the comfortable patterns of Newtonian mechanics. Energy rises with the square of velocity, and although that rise can become significant, it remains conceptually familiar. Relativistic motion changes the pattern. As a spacecraft accelerates toward the speed of light, each additional increase in velocity demands disproportionately more energy than the last. The increase is not merely large, it becomes severe enough that the final approach toward light speed turns into an endless struggle against the structure of space-time itself. The ship never reaches the barrier, but every fraction gained near it becomes dramatically more expensive. This is the reason the light speed limit is not only a conceptual boundary, but a practical one. The universe does not simply forbid crossing it. The universe makes approaching it increasingly costly, until the required energy grows beyond anything ordinary civilization can supply. Even a small spacecraft becomes an energy problem of astonishing scale once relativistic speed is involved. To accelerate a modest probe to a high fraction of light speed would require an amount of energy comparable to vast natural processes. For a vessel capable of carrying human beings, life support, shielding, and structural mass, the numbers become still more punishing. The craft is no longer just a payload, it is a world in miniature, and every kilogram of that world must be driven toward relativistic speed. Worse still, acceleration is only half the problem. If the traveller hopes to arrive rather than simply fly past the destination, the spacecraft must also decelerate. That means paying the energy cost twice for a one-way mission that ends in arrival, and 4 times for a journey that includes both departure and return with stopping at each end. The farther the dream expands, the more its energy budget grows into something that begins to resemble stellar accounting rather than engineering. This is why relativity offers permission without generosity. It says the journey is possible in principle, but it does not say the universe will subsidize it. The price must still be paid. Energy and mass are linked through the deep equivalence at the heart of modern physics. Matter stores tremendous energy, and high-speed travel demands access to that stored energy on scales far beyond chemical combustion. This is why ordinary rockets fail so early. Their energy source is too weak. Even nuclear processes, which dwarf chemical reactions, begin to look modest when the goal is to accelerate a substantial human vessel to a speed where time dilation becomes dramatic. A ship moving at 10 or 15% of light speed is already an almost unthinkable technical achievement. A ship moving at 90% belongs to a still harsher regime entirely. This does not mean the physics is uncertain. The physics is painfully clear. It means the engineering must somehow find, contain, direct, and survive levels of energy that no existing transportation system has ever approached. The challenge is not merely producing power, it is producing it in a form suitable for propulsion, delivering it with extraordinary efficiency, and managing all the consequences that follow from such concentrated power. Heat becomes a problem, waste energy becomes a problem, structural stress becomes a problem, shielding becomes a problem. Even the fuel itself becomes a burden, because fuel has mass and must also be accelerated. The familiar rocket trap returns in a new form. One wants energy to move the ship, but carrying the source of that energy adds to the ship's mass, which increases the energy needed to move the whole system. Relativistic travel therefore demands not just vast energy, but extraordinary energy density. A civilization trying to build such ships would not merely need better engines, it would need access to forms of power generation and storage that stand far beyond current practice. Human tolerance introduces another layer to the price. Acceleration cannot be arbitrarily violent if biological passengers are meant to survive in a normal state. A ship can in principle accelerate hard, but living bodies have limits. Sustained acceleration near the familiar pull of Earth offers one of the most natural profiles for human travel because it provides normal physical conditions inside the ship. Yet even this moderate acceleration requires immense power if it is maintained for long enough to push a vessel toward relativistic speed. The trip becomes not a brief burst followed by coasting, but an extended act of controlled expenditure on a scale that only increases as velocity climbs. The miracle of time dilation is therefore balanced by a brutal economy. The universe allows the traveller to age slowly relative to home, but it demands an enormous payment in energy to grant that privilege. This also explains why the gap between current spacecraft and meaningful relativistic travel is so much wider than it first appears. It is not just a matter of multiplying present performance. The difference between today's fastest probes and a ship moving fast enough for strong time dilation is not incremental. It is civilizational. It marks the difference between using local tools and commanding power on a scale that begins to rival planets, stars, or long epochs of industrial output. The traveller can go far in one lifetime only if someone, somewhere, has learned how to spend energy on a level that present humanity has barely begun to imagine. The loophole in time exists, but it is guarded by a price so high that physics itself seems to demand seriousness before allowing passage. A human being travelling at relativistic speed would not simply be moving fast through empty space. The traveller would be living inside a completely altered relationship with motion, communication, light, and matter. The ship would become not merely a vehicle, but an environment shaped at every moment by the consequences of extreme velocity. This matters because the question is not only whether a person could, in principle, cross vast distances within one lifetime. The question is also what such a lifetime would feel like while it unfolded. The first condition is acceleration. A spacecraft does not begin near the speed of light. It must build that velocity over time, and for human beings that process cannot be arbitrarily harsh. The body tolerates some acceleration well, especially when it is steady and aligned in a way that resembles the familiar pull of gravity. This is why one-Earth gravity is often used in thought experiments about long-range travel. Under that condition, the crew could stand, sleep, eat, and move in a relatively normal environment. The ship would feel less like a falling projectile and more like a world with weight. That apparent comfort hides the scale of the undertaking. To maintain such acceleration for months would require immense energy, and to maintain it for long enough to approach relativistic speed would mean living inside a sustained act of propulsion, unlike anything in current spaceflight. Still, from the perspective of daily life aboard the vessel, this steady acceleration would make the journey physically habitable in a way sudden violent thrust never could. The travellers would live not in free fall, but in an artificial gravity created by motion itself. Yet as the ship's speed rises, the external universe would begin to transform in appearance. Light from the direction of travel would be compressed to shorter wavelengths. Stars ahead would shift toward the blue, then beyond ordinary visible colours into ultraviolet and higher energy radiation. Light from behind would stretch in the opposite direction, slipping toward red, then infrared, and beyond. The traveller would not simply look out a window and see the familiar sky rushing past. The sky itself would be remade by the motion of the ship. Even the apparent positions of stars would change. relativistic aberration would crowd more and more of the visible universe into a narrowing cone ahead of the spacecraft. The heavens would seem to gather in front, while darkness deepened behind. The grand symmetry of the night sky, so familiar from Earth, would collapse into a strange forward glare and an emptied rearward void. This altered sky would be one of the psychological signatures of the voyage. Home constellations would lose their meaning. The external world would no longer present itself in the stable patterns under which human imagination first evolved. Communication would change as severely as vision. Messages from Earth could still be sent, but they would not preserve ordinary conversation, even without extreme relativistic effects. Signals require time to cross large distances. At high speed and over great range, these delays become defining features of existence. A traveller could receive long streams of history from home, but those streams would not maintain reciprocity in any familiar sense. News, voices, art, and records might arrive from Earth. Yet the traveller's responses would reach a world already far older by the time they were received. Communication would become archival rather than conversational. It would resemble correspondence with the past or the future, never the present. For the crew, this would deepen the sense that the ship had become its own moving time island. The journey would not merely cross space. It would slowly detach the travellers from shared simultaneity with the civilization that launched them. The ship would also be moving through a medium that, though extraordinarily thin, is not truly empty. Interstellar space contains atoms, ions, dust grains, and traces of heavier material. At ordinary spacecraft speeds, this sparse matter is almost irrelevant. At relativistic speed, it becomes dangerous. Each small particle approaching the forward surface of the ship would strike with enormous energy. Matter that seems negligible at low velocity becomes a radiation hazard and a structural threat at high velocity. The faster the ship moves, the more serious this bombardment becomes. A vessel carrying humans would need shielding powerful enough to absorb or deflect a continuous storm of high-energy impacts. That shielding adds mass. Added mass increases propulsion demands. The familiar logic returns once more. Every solution carries weight, and weight always asks for more energy. Magnetic protection might help with charged particles, but neutral atoms and dust remain serious concerns. The front of a relativistic ship would be less like the bow of a vessel cutting through calm water, and more like the leading face of a machine enduring a constant microscopic barrage. Inside the ship, the demands of life support would continue with complete indifference to the grandeur of the mission. Air must be renewed, water must be recycled, food must be grown, stored, or synthesized. Waste must be managed, heat must be removed. A long relativistic journey would be not just a feat of propulsion, but a feat of ecological stability and isolation. The ship would function as a closed habitat where survival depends on systems that cannot easily be repaired from outside assistance. This is another reason such travel differs from any previous human voyage. The travellers would not be moving through a landscape where rescue, resupply, or return to port remains conceivable. They would be enclosed within a self-sustaining world whose failure could mean silence and extinction in deep space. Even with all these conditions met, the psychological character of the voyage would remain unusual. Time aboard would feel normal to those living it. Meals would follow one another, work, sleep, routine, memory, friendship, and age would still accumulate at human scale. But beyond the hull, entire eras could be passing elsewhere. Children left behind might become old, and their descendants old after them, while the traveller still experiences a single coherent mission. This mismatch between lived time and outside time would shape identity as surely as acceleration or shielding. The ship would carry not only bodies across distance, but histories away from one another. A relativistic traveller could remain physically alive within one lifetime while becoming historically separated from everything once called home. The journey would therefore be survivable in biology and devastating in chronology. That is the full human texture of relativistic travel. It is not only fast, it is strange, isolating, luminous, shielded, delayed, and deeply removed from the synchronized world in which ordinary life unfolds. Beyond the engines already tested or partially demonstrated lies a set of propulsion concepts that attempt to cross the enormous gulf between present spacecraft and meaningful relativistic travel. These concepts remain grounded, at least in part, in known physics, but they demand engineering on a scale not yet achieved. They belong to the far future of serious design rather than to fantasy, and each one reveals a different way humanity might try to purchase velocity at the price relativity demands. One of the oldest and most dramatic is nuclear pulse propulsion. The idea is direct almost to the point of absurdity. Instead of releasing energy gradually inside an engine, a spacecraft would eject a series of compact nuclear devices behind itself and ride the repeated blasts forward. A large pusher plate would absorb momentum from the expanding plasma, while shock absorbers would smooth the violent impulses into a tolerable acceleration. During the 20th century, this idea was studied under Project Orion, not as fiction but as engineering. Small-scale tests with conventional explosives showed that the general principle could work. The attraction of nuclear pulse propulsion lies in the sheer energy density of nuclear reactions. Chemical fuels are far too weak for interstellar ambitions, but nuclear explosions contain enough concentrated power to raise the question again in serious form. In principle, such a spacecraft might reach several percent of light speed, perhaps more under ambitious assumptions. That would still leave nearby stars far away in ordinary time, yet it would shift the problem from tens of thousands of years towards centuries, and for robotic or multi-generational missions that change is profound. For a single lifetime, however, even these enormous blasts do not yet provide the decisive breakthrough. Another path rises from fusion, the same broad process that powers stars. Fusion propulsion would attempt to release energy by combining light atomic nuclei, producing far more energy per unit mass than chemical reactions can provide. Several serious studies have explored how a fusion-driven craft might work, often using pellets of fusion fuel ignited in rapid sequence and directed through magnetic systems to create thrust. The Daedalus study of the 1970s remains one of the most famous examples. It imagined a vast, highly specialized probe using staged fusion propulsion to reach a nearby star within a human career, or at least within the life of one scientific enterprise. A later successor effort, Project Icarus, revisited similar ideas with updated assumptions. Fusion is attractive because it promises a level of energy density much closer to what relativistic travel needs. While still resting on physical principles humanity already understands. Yet understanding is not possession. Controlled fusion for propulsion remains beyond present capability, and even if achieved, the ships would likely be enormous, their fuel mass immense, their engineering severe. Fusion may open the road to 10 or perhaps 20% of light speed under advanced assumptions, which would transform robotic exploration and perhaps allow very long human voyages. But the dramatic time dilation needed to compress interstellar journeys into modest personal years generally requires still higher speeds. Antimatter propulsion moves into an even more extreme region of possibility. When matter meets antimatter, both annihilate and convert their mass into energy with extraordinary efficiency. No known fuel source surpasses this in raw energy density. In principle, antimatter could power engines with exhaust velocities vastly greater than chemical or even many nuclear concepts. A relativistic spacecraft driven by antimatter no longer seems absurd in the equations. It becomes one of the few known pathways by which a human vessel might someday reach a speed where time dilation is not just noticeable, but transformative. The difficulty is production and storage. Antimatter does not sit in natural reservoirs ready for collection. It must be manufactured in minuscule quantities at enormous energy cost. The amounts humanity has ever produced are tiny beyond intuition when compared with what a spacecraft would need. Storage is equally difficult because antimatter vanishes in contact with ordinary matter, forcing it to be trapped by magnetic systems in near-perfect isolation. Antimatter therefore stands as a kind of theoretical gold standard, physically powerful, conceptually clear, and operationally far beyond current civilization. It shows that physics does permit engines of almost unbelievable performance, while also showing how far human industry remains from using them. A different family of ideas tries to solve the propulsion problem by moving the power source off the ship. Beamed energy systems, especially laser-driven sails, do not ask the spacecraft to carry all the energy it will use for acceleration. Instead, a powerful beam from the departure system pushes on a reflective sail, steadily transferring momentum from afar. This idea has received serious modern attention because it avoids one of the deepest burdens in rocketry, carrying the fuel that must itself be accelerated. In this arrangement, the ship can be much lighter because the energy infrastructure remains at home. For very small probes, the concept is especially promising. A light sail driven by a vast laser array might reach a significant fraction of light speed, enough to send instruments toward nearby stars within decades. For human travel, the difficulty becomes deceleration, habitat mass, shielding, and control. A lightweight robotic sail can survive as a fast flyby. A human vessel must slow down, protect its occupants, and remain habitable. Still, the principle is important because it breaks the closed loop of onboard fuel burden. It suggests that an advanced civilization might someday build propulsion architectures spanning planets or entire inner solar systems, using fixed energy infrastructure to launch interstellar craft outward. The engines of the far future therefore divide into several broad strategies. One uses violent nuclear pulses to trade political and engineering difficulty for raw impulse. Another uses fusion in the hope of harnessing stellar fire in controllable form. A third turns to antimatter, the most energy-dense fuel known, while confronting almost impossible production challenges. A fourth leaves the energy source behind and pushes spacecraft remotely with concentrated light. None of these concepts is easy. None presently carries human beings between stars. Yet unlike ordinary rockets, they occupy the correct scale of seriousness. They acknowledge that interstellar travel within one lifetime demands not a better version of familiar machines, but propulsion systems closer to cosmic engineering than to transportation as it is now known. At the far edge of serious propulsion studies, the line between engineering and speculation begins to blur. This region is important because it shows how human thought behaves when confronted with distances that seem to defeat every ordinary machine. Some ideas in this region still cling tightly to known physics, though in difficult or hostile forms. Others lean into mathematical possibilities that may never become physical technologies. What unites them is not practicality, but the attempt to imagine what lies beyond rockets as they are now understood. One such concept is the interstellar ramjet, often called the Bussard ramjet. Its appeal is immediate. Instead of carrying enormous quantities of fuel, a spacecraft would sweep hydrogen from the interstellar medium using vast magnetic fields and fuse the collected material as it moved. The ship would become, in principle, a self-feeding engine. It would harvest the medium through which it travelled and use that material to continue accelerating. For a time, this idea seemed almost ideal. It promised a way around the fuel burden that destroys so many rocket designs. But closer analysis revealed a harsh difficulty. Interstellar space is not empty, yet it is extremely thin. Collecting enough material to matter would require a magnetic scoop of staggering scale. Worse, the very act of gathering particles would create drag. And in many realistic analyses, that drag grows too large for the engine to overcome. The concept is elegant, but elegance does not guarantee survival under detailed physics. In most ordinary interstellar environments, the ramjet appears unable to deliver the indefinite acceleration once hoped for. It remains a valuable lesson in the difference between a beautiful idea and a workable one. Hybrid concepts try to keep that lesson in mind by combining multiple methods instead of asking any one system to solve every stage of the journey. A spacecraft might use a beamed laser or microwave system for initial acceleration while still near home, then rely on onboard fusion or another advanced engine for later maneuvering and deceleration. Or it might use a powerful departure system and then deploy a magnetic sail near the destination, attempting to break against the interstellar medium or the stellar wind of the target star. These combinations are attractive because they divide the problem into phases. Launch from home need not use the same logic as arrival at the destination. A mature interstellar civilization, if one ever emerges, may build not a single perfect engine, but an ecosystem of propulsion methods matched to different stages of travel. Even so, these remain extraordinarily demanding systems. They do not remove the need for huge energy, strong materials, reliable shielding, and stable life support. They only rearrange which burden appears at which point in the mission. Then there are the concepts that step beyond difficult engineering and into uncertain physics. The warp drive is among the most famous. In the version proposed within general relativity, space itself would be contracted ahead of a vessel and expanded behind it, allowing the craft to ride a distortion of space-time rather than move locally faster than light. Inside its own bubble, the ship would remain at rest relative to nearby space, while the surrounding geometry carried it along. The attraction of this idea is obvious. It seems to offer a route around the light speed barrier without violating relativity directly. The mathematics, in certain forms, can be written down. But writing equations is not the same as building a machine. The known versions of the concept require exotic conditions, especially negative energy density, that may not be physically available in the needed form or scale. Some calculations also imply absurd energy requirements, sometimes on planetary or even greater scales. The warp drive therefore occupies a peculiar status. It is not pure fantasy in the sense of ignoring known theory, but it remains profoundly disconnected from any credible engineering path. Wormholes occupy a similar territory. General relativity allows solutions in which distant regions of space-time are connected through a shortcut, so that a traveller entering one mouth emerges far away without crossing the full intervening distance in the normal way. If traversable wormholes existed and could be stabilized, they would transform the meaning of distance more radically than any engine. A star or galaxy could become a door away rather than a voyage away. Yet again the mathematics appears more generous than the physical world. Stable traversable wormholes seem to require exotic matter or negative energy conditions that remain hypothetical. Even if those obstacles were somehow overcome, there remains the practical question of how the wormhole mouths would be placed in useful locations to begin with. A shortcut is only helpful if its ends are already where one needs them. Otherwise, the original propulsion problem returns in disguised form. These speculative concepts reveal something important about the human response to vastness. When ordinary machines fail, the imagination turns to deeper levels of physical law and asks whether space and time themselves might be engineered. That move is intellectually natural, but it must be handled carefully. Known physics does not currently forbid every strange geometry the equations can describe. It also does not guarantee that those geometries can exist as usable technology. In this region, possibility becomes layered. Mathematical consistency is one layer, physical existence is another, engineering feasibility is another still. Most speculative travel concepts have not climbed successfully through all three. What remains most credible, for now, is that the future of interstellar travel will likely depend on advanced but still sublight propulsion fusion, beamed energy, hybrid systems, perhaps antimatter if civilization becomes vastly more capable. These may never yield the effortless passage imagined in fiction, but they fit more honestly within the known structure of nature. The speculative ideas remain useful not because they are ready for construction, but because they illuminate the outer edge of what theory presently entertains. They show that the imagination has not stopped at better rockets. It has followed the problem all the way to the architecture of space-time itself. Whether those deeper roots will ever open remains uncertain. For now, they serve as mirrors reflecting both human audacity and the stubbornness of the universe. When the question shifts from engines to the structure of the universe itself, the scale of travel changes again. Up to this point, the problem concerns propulsion, energy, and the strange flexibility of time near light speed. Now another fact enters the picture. The universe is not static. It is expanding. Galaxies on the larger scales are not sitting motionless inside a fixed cosmic container. Space itself stretches, carrying distant structures farther apart over time. This means the map through which any future traveller moves is not standing still while the journey takes place. The road is changing as it is crossed. This expansion was one of the great discoveries of 20th century cosmology. Observations show that distant galaxies are generally receding from one another, and the farther away they are, the faster that recession becomes. The image often used is that of points on a swelling surface, though no simple image captures the full geometry. What matters here is not the metaphor but the consequence. Distance on the larger scales is dynamic. A traveller does not move through an eternal fixed stage. The stage itself expands. That expansion alone would already complicate the idea of ultimate reach. But the story goes further. Late in the 20th century, astronomers discovered that the expansion of the universe is accelerating. Some unknown component, often called dark energy, appears to dominate the large-scale dynamics of cosmic expansion in the present era. This does not merely stretch distances, it changes the long-term fate of what can ever be reached. The observable universe is often mistaken for the reachable universe, but the two are not the same. The observable universe is defined by what light has had time to bring to Earth since the early cosmos became transparent. That sphere extends enormously far in every direction, with a radius of roughly 46 billion light-years. It contains galaxies whose ancient light is arriving only now, after billions of years of travel through expanding space. Human instruments can observe these remote structures, which creates the natural impression that they belong, at least in principle, to the domain of future exploration. But observation is not access. Many things can be seen whose present locations or future histories are not reachable by any traveller departing today. The distinction arises because the universe has been expanding the whole time their light was en route. A galaxy whose light began travelling when the universe was young may now be vastly farther away than the simple age of the universe would suggest. The photon arrives because it was emitted long ago under different cosmic conditions, not because the source remains nearby in any practical sense. This leads to a more important boundary for travellers, the cosmological event horizon. This horizon marks the farthest distance from which anything departing now, even at the highest speed allowed by known physics, could ever influence or reach us in the future, and likewise the farthest distance we could ever hope to reach by setting out today. Beyond that boundary, cosmic expansion wins permanently. Space stretches too quickly on the large scale for any ship or signal to close the gap. This is not because galaxies beyond that horizon are doing something forbidden in their local frames. It is because the geometry of the expanding universe prevents contact across those immense separations. The event horizon therefore defines a hard outer limit more profound than the light speed barrier alone. Even if perfect propulsion existed, even if a ship could accelerate to an arbitrarily close approach to light speed and sustain it, not every visible destination would be reachable. Some are already lost in principle. This changes the emotional meaning of cosmic travel. Earlier, the stars and galaxies seemed distant but not conceptually forbidden. Relativity and propulsion offered routes, difficult but real. Cosmic expansion now reveals that the universe itself withholds much of what it displays. Light from remote galaxies can enter the telescope and still come from places no traveller will ever touch. The cosmos becomes, in part, a gallery of inaccessible shores. And because expansion is accelerating, this accessible region is not growing more generous with time. In an important sense, it is shrinking as a fraction of the whole. More and more distant structures will eventually slide beyond practical contact forever. Over immense future timescales, observers in the descendants of the Milky Way may see fewer galaxies than humanity sees now. The universe available to view and the universe available to reach are both historically contingent. Humanity lives in a window during which the larger cosmic structure can still be observed in rich detail. That window will not remain open indefinitely. For travel, the implication is severe but clarifying. The question of how far a human could travel in one lifetime cannot be answered by looking only at ship speed and subjective time. The destination itself may be moving away through expanding space in a way that changes whether the journey is possible at all. Near stars inside the Milky Way are unaffected in any practical way by cosmic expansion, because local gravity binds the galaxy together. Nearby galaxies in the local group are similarly governed by local gravitational structure more than by the general expansion. But on sufficiently large scales, expansion dominates. The farther outward the ambition reaches, the more cosmology takes command from engineering. This means the ultimate range of human exploration is set by two very different kinds of law. Relativity governs the traveller's motion and time. Cosmology governs the evolving geometry of the destination. One tells how a lifetime can stretch. The other tells which parts of the universe remain open to such stretching at all. Together they create a picture that is both generous and austere. The universe permits far more travel than ordinary intuition would guess, yet denies access to much of what it reveals. The stars may someday become roads. Many galaxies never will. The map of possibility is therefore not only large, it is bounded, historical, and already changing. Within the limits set by relativity and cosmic expansion, the question of ultimate range can now be stated more clearly. How far could a human actually travel in one lifetime if propulsion were no longer the main obstacle, and velocity could be pushed to the highest physically meaningful levels below the speed of light? The answer depends on which lifetime is being measured. In the frame of Earth or any stationary outside observer, the journey remains long. In the frame of the traveller, the range grows astonishingly. This distinction is now the central fact. A lifetime lived aboard a relativistic ship can encompass distances that would otherwise seem forever outside the reach of one biological existence. The smallest dramatic examples appear within the local region of the Milky Way. At 99% of light speed, a traveller's time is already compressed enough that a voyage spanning hundreds of light years can fit within a single personal lifetime. From Earth's perspective, centuries pass. From the ship's perspective, the journey can remain within decades. That means a traveller could cross a large volume of the local stellar neighbourhood, visiting regions containing tens of thousands of stars, nebulae, clusters, and planetary systems, while still living a human-scale span of years aboard the vessel. Push the speed closer to light, to 99.9% or beyond, and the accessible radius expands sharply. Distances of around 1,000 light-years begin to fit inside a few decades of subjective time. The Orion region, rich with star formation and luminous gas, moves from abstract astronomy toward lived destination. The traveller could, in principle, witness structures that on Earth appear only in telescopes and long-exposure images, not as faint marks of light, but as surrounding environments. At still higher relativistic factors, the journey reaches deeper into the galaxy. The great star-forming regions of Carina and the Eagle Nebula, thousands of light-years away, begin to enter the range of an extended but still recognizably human lifespan, measured on board a sufficiently fast ship, the galactic center, which ordinary intuition places beyond all personal reach, no longer remains forever closed in principle. At velocities fantastically close to the speed of light, the traveller's proper time can shrink enough that a trip of tens of thousands of light-years becomes a matter not of geologic ages, but of a severe life trajectory. A person might leave one quiet spiral arm environment and arrive at the black hole-rich inner regions of the galaxy without personally enduring the full 26,000 years that Earth would count. The price, however, is historical separation. The farther the traveller goes, the less likely any recognizable return becomes. If one lifetime is used for one-way travel only, then the map grows far wider than most first assume. Even the outer Milky Way can, in principle, fall within the range of a single life aboard an extreme relativistic craft. A human being could cross from the Sun's neighbourhood toward the galactic centre, or beyond it toward the far side of the disk, and still age by a finite personal span rather than by the full galactic crossing time measured from Earth. The galaxy ceases to be an uncrossable island and becomes, at least in theory, a place through which one conscious life could move. The same reasoning extends to the satellite galaxies of the Milky Way. The large Magellanic Cloud, the small Magellanic Cloud, and several dwarf galaxies orbit at distances that are enormous by ordinary human standards, but still tiny compared with the full scale of the universe. With sufficiently extreme relativistic motion, a traveller's lifetime could encompass voyages to some of these neighbouring systems. The shipboard years might remain within a long but finite life, while outside history advances by tens or hundreds of thousands of years. These journeys would already be so temporally isolating that they would function more like migration into remote futures than exploration in any ordinary sense. Yet physics does not forbid them. The range continues outward. The Andromeda Galaxy is the great symbolic threshold, at about 2.5 million light-years away. It represents the nearest major spiral galaxy beyond the Milky Way. Reaching it within one subjective lifetime would require truly extreme relativistic motion, with the traveller moving so close to light speed that the difference becomes almost inaccessible to ordinary intuition. Yet the equations continue to allow it. In traveller time, Andromeda can be drawn inward dramatically. A person could, in principle, leave the Milky Way and arrive in another major galaxy within one lived life. Though Earth and everything familiar would age by millions of years during the crossing, the journey would not be a visit in the historical sense. It would be an exile into another cosmic era. Beyond Andromeda lie galaxy groups, clusters, and the larger web of cosmic structure. In purely theoretical terms, if velocity could be driven close enough to the light speed limit, the traveller's proper time could remain finite even while the outside journey spans tens of millions, hundreds of millions, or more than 1 billion light-years. Great galaxy clusters such as Virgo would become destinations for one lifetime aboard the ship, though not one lifetime for the civilization left behind. At the absolute conceptual edge, the traveller could cross substantial fractions of the observable universe in personal decades if propulsion approached near-perfect relativistic capability. Yet here cosmology reasserts its authority. The event horizon remains. Some destinations, no matter how ancient their light appears in the telescope, are simply unreachable by departure today. Therefore, the ultimate reach of one human lifetime is not the full observable universe. It is the reachable portion of it, filtered through both relativity and cosmic expansion. This reachable universe is still staggeringly vast. It includes nearby stars, large parts of the Milky Way, neighbouring galaxies, and, in principle, structures on scales that dwarf every landscape human culture has ever imagined. But not everything seen is available. The ultimate range is immense without being infinite. It is one of the strangest conclusions in science. A single biological life, if joined to sufficiently powerful motion, could stretch across distances that ordinary intuition reserves for civilizations, species, or myth. Yet even that enlarged life remains bounded. The universe opens almost everything and withholds the rest. At the outer edge of the question, the limit is no longer speed alone and no longer distance alone. It becomes a human limit shaped by meaning. Physics permits astonishing reach, but it does not guarantee return in any form that preserves belonging. This is the final consequence of everything that comes before. A human being may, in principle, travel across vast portions of the galaxy, perhaps to neighbouring galaxies, perhaps farther into the reachable universe, all within one subjective lifetime if the ship moves close enough to the speed of light. Yet that same success turns the traveller into something like a one-way witness, a consciousness carried forward through time as much as through space. The farther the journey extends, the more completely it severs the traveller from the era that made the journey possible. This is what distinguishes relativistic travel from every great expedition in human history. Earlier voyages preserved some continuity with home. Sailors crossed oceans and returned to ports that still remembered them. Explorers moved through dangerous lands, but letters, memory, language, and political worlds remained connected across the route. Even when journeys were long and deadly, they still took place inside a shared historical present. Relativistic journeys do not protect that present. They break it. A traveller leaving Earth for a distant star at extreme speed may age only a few years or decades, but the Earth to which that traveller returns, if return is even attempted, may have moved centuries or millennia ahead. For a voyage to a cluster or a distant galactic region, the gap may become tens of thousands of years. For a journey to Andromeda, millions. The ship preserves biology while history disappears. This makes every great relativistic voyage a choice not only about exploration, but about exile. The traveller does not simply accept distance. The traveller accepts desynchronization from everyone and everything once called home. This is why the practical meaning of one lifetime depends on what kind of life is desired. If the aim is pure range, then the answer is almost unimaginably generous. One lifetime can span nearby stars, large regions of the Milky Way, satellite galaxies, and, in principle, separate galaxies far beyond the local one, limited finally by the cosmic event horizon and the expansion of the universe. If the aim includes return to a recognizable civilization, then the range collapses. A traveller who hopes to come back while language, memory, culture, and kinship still remain intelligible must stay much closer to home. In that case, perhaps the practical horizon lies within a few hundred light years, perhaps less depending on the chosen timescale of return. This is still an enormous domain, rich with stars, planets, nebulae, and possible futures of settlement. but it is tiny compared with the full reach allowed to a one-way traveller. The deepest answer, then, is not a single number. It is a spectrum shaped by values. Range opposes return. Wonder opposes continuity. Discovery opposes shared time. Physics does not decide which trade is worth making. Physics only states the terms. A person may cross to another galaxy within one personal life only by surrendering any ordinary reunion with the civilization that launched the journey. A person may remain historically connected to home only by accepting a much smaller radius of travel. There is no escape from this exchange because time dilation, though generous to the traveller, is indifferent to those left behind. The universe offers reach by charging history. This final truth gives the subject its human gravity. The most important barrier to cosmic exploration may not be propulsion, energy, or shielding, difficult as all of those are. It may be the question of what human beings are willing to become in order to travel that far. A civilization might one day possess engines powerful enough for relativistic migration. It might build ships capable of enclosing whole communities, archives, ecosystems, and lineages. It might send people outward knowing they will never again share a present with Earth. Such voyagers would not simply be astronauts. They would be founders of disconnected futures, seeds carried into other stellar or galactic soils. Their relationship to humanity would resemble ancestry more than participation. They would descend from Earth without continuing within Earth's historical now. That possibility is both magnificent and lonely. It suggests that the universe is open, but not intimate. It permits movement across astounding scales, but often only by dissolving the bonds that give movement personal meaning. Even so, this does not diminish the grandeur of what physics allows. On the contrary, it clarifies it. The laws of nature do not imprison life on one world forever. They permit consciousness to stretch outward across distances once thought forever inaccessible. They allow one living being, carried by enough speed, to witness parts of reality that seem to belong only to remote observation. The stars are not forbidden. The galaxies are not wholly closed. The road exists, but it is a road through time as much as through space, and every mile gained outward may mean an age lost behind. So the ultimate answer is both immense and intimate. A human could travel astonishingly far in one lifetime, perhaps across the galaxy, perhaps beyond it, perhaps toward the very limits of the reachable universe, provided sufficiently advanced propulsion exists. But the farther that life travels, the less it remains part of the world from which it began. The true boundary is not merely how far one body can go before dying. It is how much separation from home, history, and shared time a human life can bear and still call the journey worth making. The question begins with engines and ends with perspective. A human life seems small when placed beside stars, and smaller still beside galaxies in the expanding universe. Yet the laws of physics do not close the road completely. They set terms. They require energy, patience, shielding, and forms of propulsion that do not yet exist in human hands. They impose the speed of light as a limit, then quietly reshape time for those who move close to it. In that strange balance, the universe reveals both restraint and permission. It denies easy passage, but not all passage. It keeps most journeys difficult, but not all journeys impossible. Within one ordinary life lived on Earth, the reachable cosmos remains narrow. Within one life lived aboard a sufficiently fast ship, the reachable cosmos grows vast. Nearby stars become destinations. The Milky Way becomes a traversable structure in principle. Even neighbouring galaxies move from fantasy toward physical possibility. But each gain in range carries a loss in shared time. The traveller who goes far enough does not return to the same world. Home moves on. history continues elsewhere. The journey stretches life outward, while thinning the thread that ties that life to its beginning. So the final limit is not only mechanical or mathematical, it is also human. The universe allows astonishing distances to fit inside one lived span, but often only by turning travel into departure without reunion. Some future travellers may accept that bargain. Others may choose nearer stars, shorter returns, and a smaller but still beautiful frontier. Both choices belong to the same truth. The cosmos is not closed, it is only vast, exacting, and patient.